Hello, this is Ryusuke Sugimoto from the University of Waterloo. In this video, I'll talk about our SIGGRAPH Asia 2024 paper, Projected Walking Spheres, a Monte Carlo closest point method for surface PDEs. I worked on this project with Nathan King, Toshiya Hachisuka, and Christopher Batty from the University of Waterloo. In this work, we present the Projected Walking Spheres method, a Monte Carlo closest point method for surface PDEs. Our proposed method solves Laplace-type PDEs on surfaces without relying on any specific surface representation. Our method is not limited by any specific resolution, and it does not require boundary conforming meshing. But why is such a method useful? Or why should we care about surface PDEs? It's because surface PDEs are common tools in computer graphics that let us perform surface editing, texture synthesis, geodesic distance computation, fluid simulation on surfaces, and solving diffusion curve problems on surfaces. When it comes to solving surface PDEs, you may think that we can use the good old Khotan Laplacian, but the story is not as simple as that. The Khotan Laplacian is applicable only to triangle mesh surfaces. For different surface representations, we need to use different discrete Laplacians. But how do we solve problems with higher order elements, parametric surfaces, or surfaces with mixed elements where multiple surface representations are used together? Additionally, discretization always comes with some discretization artifacts, and the required resolution can even vary spatially due to rendering requirements. Lastly, if we want to respect the boundary curve accurately, we would need to cut the mesh. This boundary conforming discretization is possible, but is a tedious operation. Fortunately for volumetric PDEs, there is a solution to these problems, which is a Monte Carlo method called the Walking Spheres method. The Walking Spheres method estimates the solutions to the Laplace equation with the Dirichlet boundary condition. To estimate the solution at point x, we draw the largest sphere centered at point x contained inside of the domain. The mean value theorem tells us that the solution at point x is equal to the average of the solutions on all the points on this sphere. We thus uniformly randomly sample a point on this sphere as an estimate. We still don't know the solution at this point either, so we repeat the process until the sample point is within an epsilon distance from the boundary. We then use the given boundary value at the closest boundary point as the sample path contribution. This is how we get one sample, and we repeat the process many times and take the average sample path contributions to get the converging estimate of the solution. This Walking Spheres method is agnostic to the representation of the boundary. It is resolution-free, and it does not require any boundary conforming meshing of the domain. However, Walking Spheres is applicable to volumetric PDEs only. We thus aim to generalize the Walking Spheres method for surface PDEs by borrowing an insight from another method, the closest point method, which is an embedding method for surface PDEs. The closest point method computes the solutions to the surface Laplace equation with some boundary condition such as the Dirichlet boundary condition. Note that the volumetric Laplacian is replaced with the Laplace-Beltrami operator or simply surface Laplacian. In this illustration, we have a 1D surface in the 2D domain. First, we compute the medial axes of the surface and consider a neighborhood around the surface such that this space does not intersect with the medial axes. Then, we introduce the closest point extension, which extends the solution on the surface to this neighborhood embedding space. We define the extended solution EU in the embedding space to be equal to the solution on the surface at the projected point. With this closest point extension, we find some nice properties, which is that on the surface, the volumetric Laplacian applied to this extended solution is equal to the surface Laplacian applied to the original solution defined on the surface. More generally, in the neighborhood of the surface, we can also expect this equality to hold approximately. This means that we can solve surface PDEs by replacing surface operators with volumetric operators in the embedding space. The traditional closest point methods construct a system of linear equations by discretizing the embedding space with a grid or particles. The closest point method is designed for surface PDEs, and it is actually agnostic to the representation of the surface because all we need is the closest point query to the surface. However, we still have resolution issues due to the discretization of the embedding space, and dealing with boundaries is a little tedious. Still, this idea of the closest point method is the inspiration of our new algorithm, projected walking spheres. The projected walking spheres method generalizes the walking spheres method with the theory of the closest point method. The projected walking spheres estimates the solutions to the surface Laplace equation with the Dirichlet boundary condition. First, we compute the medial axes of the surface. Also, we extend the boundaries of the surface to their normal directions. To estimate the solution at point x, we draw the largest sphere centered at point x that does not intersect with the medial axes. In the neighborhood of the surface, we can use a volumetric relationship for the Laplace equation, so with the volumetric mean value theorem, we uniformly sample a point on this sphere as an estimate. The extended solution at this point must be equal to the solution on the surface at the projected point, and we enforce this closest point extension requirement by projecting the walk to the surface. We repeat this process until the sample point is within an epsilon distance from the extended boundary. We then use the given boundary value at the closest boundary point as the sample path contribution. We gather many samples this way and take the average of them to get a converging estimate. This is how projected walking spheres works. Our method is surface representation agnostic because all we need is the closest point query to the surface. In this example, we solve the diffusion curve's Laplace problem on the surface, where the surface is represented with a combination of triangles, oriented points, and even codimensional rods. Our method supports view-dependent evaluation. We cast rays from the camera to choose the solution evaluation points, so the solution is not limited by any specific surface discretization resolution. We also do not discretize the surface in a boundary conforming manner in this example. If a discrete basis is available, our method can utilize that to filter the solution on the surface to get a less noisy solution. We use this filtering method in this example scene with a quad mesh surface. We can generalize projected walking spheres to Poisson equations and gradient estimates, which enables these geodesic distance computations. Our method can also solve the screened Poisson equation. We apply an implicit time integration to the wave equation to get the screened Poisson equation and then solve it with our method. Lastly, our projected walking spheres method has a few open problems. We currently support Dirichlet boundaries only, and solving Neumann and Robin boundary problems efficiently remains an open problem. When we take walks, we set a small lower bound for the sphere radius so the walks would not get stuck, but this implicitly smoothes sharp corners in the geometry. Around the neighborhood of the surface, the equality relationship between the volumetric Laplacian and the surface Laplacian holds only approximately, and we introduce some bias because the algorithm ignores this inequality. Incorporating an error compensation term in our computation would further improve the reliability and broaden the applicability of our method. In summary, our projected walking spheres method is a generalization of the walking spheres method for Laplace-type surface PDEs with the theory of the closest point method. Our method is a surface representation agnostic and resolution-free method with no boundary conforming discretization. We also developed a discrete basis-based filtering method and extensions of projected walking spheres for various equations. Thank you very much for watching this video, and if you have any questions, please contact me via email.